Now let's take a look at another main advantage of our feedback amplifiers, our bandwidth extension. So in order to look at this, let's assume that our frequency response for a simple amplifier can be characterized by a single pole system. So assume our frequency response of our basic amplifier, which we've looked at previously with that block diagram configuration, can be characterized by a single pole. And so what that looks like in terms of our transfer function is we have A of S is equal to A naught divided by 1 plus S divided by omega H. And so I've thrown in a lot of new stuff here, so let me sort of summarize some of these ideas and make sure everybody's on the same page. So here I'm saying that S is equal to J omega. So this implies that we have some type of frequency information going on, and of course that's relevant because we're not always going to be dealing with DC signals. In fact, more often than not, we're going to be dealing with something that has some frequency. So the other thing is this A naught term. And so this A naught term is going to be our low frequency or our mid-band gain. So mid-band gain. And then this WH we can think of as our upper 3 dB frequency. So upper 3 dB, which we can also call our corner frequency. And so if we plot what this looks like on a plot, let's do a plot here of our gain versus frequency. Okay, so let's say we have our frequency omega in radians per second on our independent axis, and up here we have the magnitude of our gain. So what we're saying is for this open loop configuration, we're starting out somewhere up here with an open loop gain of A naught. So that's our low frequency or mid-band gain. And so we're going to be maintaining that frequency up until we get to some corner frequency. And so from our Bode plot approximation, we say after this point, our WH, we're going to be decreasing at negative 20 dB per decade. And so we're not too worried about that just yet. We'll get into that a little bit later on. But basically, we're just decreasing our gain. Let's say it looks something like that. And so, of course, we're not going to have this sharp decrease. In reality, it's going to be a more sort of curved transition. So let me just draw that briefly. So maybe we'd see something more along the lines of that in real operation. But this gives us a good approximation. So we're talking about our bandwidth extension. And so, of course, we're talking about bandwidth extension as we use feedback in our circuit configuration. So let's express our closed loop circuit gain for this open loop expression here. So let's take this expression and let's determine what our closed loop gain would be. So our closed loop gain can then be expressed as A sub f, which is a function of S, which remember is J omega. So that's of course just going to be A of S divided by 1 plus beta times A of S. So that's because we're still just using that basic feedback topology from last time. So something that we can keep in mind to make this a little easier is we can remember that up here, this S over omega H is actually just our beta A naught. Okay, so now coming down here, we can rewrite this then as, so in our numerator, we're going to have A naught divided by 1 plus beta A naught. And all of that is going to be divided by 1 plus S divided by omega H times 1 plus beta A naught. All right, so we get this big mess here. But of course, we can sort of compare these two equations. We can compare this equation for AF with our initial equation up here for our open loop gain A. And we see we have our low frequency or mid-band gain in the denominator. So let me erase this highlighting. So let's say we have our low frequency gain here. Well, if we compare that to this equation here, we see that corresponds to this right here. So now our low frequency or midband gain is A naught divided by 1 plus beta A. So if we're going to draw this on the same plot, we maybe have it down here, A naught divided by 1 plus beta A naught. So we've decreased our gain, which we already expected, right? We said if we employ feedback, we are decreasing the gain of the system. Okay, so the next thing we want to look at is sort of that corner frequency. So we see from this expression, our corner frequency was this omega h. So it's 1 plus s divided by omega h in the denominator. So let's compare that to this expression. So we have 1 plus s divided by some stuff. And so basically all this stuff then is our new corner frequency. So we see that's going to be omega h times this 1 plus beta A naught factor, and that's going to end up being larger than our initial corner frequency. So we have something that looks like this. So maybe we can write that as being over here. So this is omega h times 1 plus beta A naught. So that's going to be our corner frequency, and I just about drew that right. And so if we want to draw this curve, we're starting at this gain here, and we're coming out till we get to this corner frequency. So if we're doing sort of this Bode plot approximation, then our gain just immediately starts decreasing there. Of course, it'll be sort of a curved transition, but we get something that looks like this. And so this blue then is our closed loop, and the red is our open loop. And so this sort of supports what we've seen before, in that for our open loop we have a higher gain, for our closed loop we have a lower gain. But we notice that in our closed loop configuration we can operate up to much higher frequencies before we see drop off in our gain. One other thing that we want to mention related to this is our gain bandwidth product. And so we're going to look at that for both of these two configurations. And so as the name implies, we're just going to multiply the gain by our bandwidth. So let's look first at our open loop case. So for our open loop case, our gain, and we're talking about our small signal or midband gain, was A naught. And our bandwidth, as a first order, we can say our bandwidth is the frequency up to that 3 dB frequency, which is the omega h. So for our open loop case, it's A naught times omega h. So simple as that. Okay, so now let's look at our closed loop case. So for our closed loop case, we can see here highlighted in orange, or if we come up to our plot, we see it here as well. Our low frequency or midband gain is this A naught divided by 1 plus beta A naught. So we have A naught divided by 1 plus beta A naught. And our bandwidth is now going to be omega h times the quantity 1 plus beta A. So omega h times the quantity of 1 plus beta A naught. And so what we see here is this 1 plus beta A naught is going to be canceling out, and we're left with the exact same A naught omega h. And so what this tells us is that our gain bandwidth product should be constant for a given system. So our gain bandwidth product is constant for a given system. And so what that tells us is that if we want to increase our gain, we do so at the expense of bandwidth. So if we send one up, the other comes down. So we could increase our bandwidth, but that means we decrease our gain. So again, we're talking about all these trade-offs as we're designing our system.